Very much, Jörg. So first, let me start. Can you hear me? Is it working? Okay. So first, let me start by warmly thanking the organizers of this wonderful workshop. It's really a pleasure to be back in person in a community of real people with whom we can have real discussions. It's really great. And it's always fun to be at this SPICE workshop. It reminds me, reminds me of being in the film Dune, you know. So let me try to give you some SPICE here. Okay, so my talk is about frustration and correlations. And there are basically two messages to the talk. The first one is that by sort of combining the effect of strong correlations with frustrations in particular, but not only geometric frustration, one can actually reveal really interesting phenomena. And I also, as a general message, would like to convince you that theory is sometimes a little useful and that there has been quite a bit of progress over the last couple of decades on actually handling this complicated quantum anybody problem. So I've packed probably a little bit too much into this talk. Let's see until what point I manage to go. First, I would like to give you some motivation why combining these two things of strong correlations and frustration leads to interesting things. Well, maybe there is sort of a mundane reason, which is that when you have a complex problem, just make it more complicated. Maybe you'll be able to get somewhere. But there is actually there are actually deeper reasons. One of the important reasons for which introducing frustration in the game is a good idea is that at a certain level, ordered phases are a pain in the neck. If you think from a high temperature perspective, there are crossovers as you increase the strength of interaction, which is going to take you from a metal to a Mott insulator at high temperature. This is likely to be a crossover, but a rather interesting and complex one, as we're going to see at some point in this talk. You may reach some sort of critical behavior that I will describe later, where there is a first order transition line and a critical endpoint. We know that this does happen in real materials like the BDT organics or some oxides like V2O3. But then at some point, this interesting state, which is a Mott state, meaning that the electrons are localized, that the spins are still fluctuating somewhat. So in this regime, you would have some sort of Curie-Weiss susceptibility. And at some point, these spins have to do something. So in a system without frustration, what they're going to do is they're going to just order magnetically. And in many cases, this ordered phase is so prominent, meaning so unfrustrated, that the transition temperature is very high. So in a very unfrustrated system, the transition temperature, this red phase, would be something like this. And it will obscure many of the interesting phenomena that happens here. You will see, of course, important crossovers at high T. But in systems with a lot of frustration, you can actually suppress this transition temperature into an ordered phase. Aspects of the Mott phenomenon. Of course, fluctuating spins can't fluctuate forever as you go down to low T. And something must also happen. In the most interesting and unusual cases, what will happen is instead of ordering, the system will go into some sort of spin liquid state. And so that makes it even more interesting. So this is one motivation, which is sort of use frustration to put forward the Mott phenomena in its pristine form. And there are many examples of this to which I will come back later in the talk. I'll just flash a few slides and then I will come back on these examples later in more detail. For example, some quantum critical scaling associated with the Mott transition has been revealed, as I'm sure you know, in these organic materials that we are all interested in this workshop, in the group of Kanoda Sensei. And more recently, so these are the sort of triangular materials that we all love. And you see here, and I will come back to this, that these materials have for the cyanide material, a crossover as function of a transition as function of pressure between a quantum spin liquid and a metal ending into a critical point. But then at higher temperature, there are very, very interesting crossovers that apparently are based on quantum critical scaling, and I will come back to that later in the talk. More recently, there's been a whole new zoo of materials in which we can explore this competition or this synergy between strong correlations and frustrations. And this is the field of transition metal dichalcogenides. These are, if you want, to a certain extent, on-demand quantum systems in which you can tune a lot of parameters. So the second part of the talk will actually not deal with molecular organics, but deal more with these TMDCs. And there could be TMDCs, mostly bilayer TMDCs. There could be homobilayers, like in this paper from the Cornell group, which realizes a moiré system without any twist, just because there is a lattice mismatch between sorry, I put the wrong picture in, no, this one, okay, here. This is an hetero-bilayer system in which there is a lattice mismatch between the tungsten diselenide and molybdenum ditelluride, and as a result, a moiré pattern forms. You can also study that, and this is a recent paper from the Columbia group, in which you have an homobilayer tungsten diselenide, but then you twist the two layers and generate a moiré pattern. So you see these two papers appeared more or less almost in the same issue of Nature, and they both address the question of sort of revealing genuine aspects of the Mott transition, and both are a triangular lattice, as you see probably from this pattern of the moiré pattern. Okay, there is another motivation besides this question of sort of revealing the genuine aspects of the Mott transition to study frustrated and correlated systems. And I already alluded to it. The reason is that when you go now to low temperature in a frustrated system, more unusual phases than a good old ordered antiferromagnet, let's say, appear. It's well known that in some of these BDT materials, you get spin liquid states, for example, instead of ordered phases. And of course, you also get unconventional superconductivity, whose nature is still not entirely understood. Sometimes, actually, very interestingly, having a transition from a rather bad metal into a superconductor, instead of having a transition between a metal where there are nice coherent quasi-particles into a superconductor, which is sort of the standard model of the superconducting transition in good textbooks. Okay, so these were just a few slides of very general motivations, the genuine aspects of the Mott transition and exotic phases at low T. So now I'm going to spend a few minutes going back in a little more detail on materials. So of course, the family of the 2D organic superconductors do not need a long introduction in this workshop, so I will just flash basically only one slide. And for each of these family of materials, I want to emphasize what is the relevant model, and I'll focus on materials that have triangular lattices. So this workshop is almost entirely devoted to this family of 2D organic conductors and superconductors, the ET salts. You all know the story. They form dimers in the kappa ET family. The molecules come in pairs and they are staggered in this checkerboard pattern. And you can simplify, as theorists like to do, the problem at low energy, and also worked on that several years ago in quite a bit of detail, to a triangular lattice Hubbard model, which is, however, anisotropic, with the hopping T prime here being different from the hopping on the underlying square lattice, which is T. Of course, when T prime is of order T, we have the ordinary isotropic triangular lattice, which is sort of maximally frustrated. And these are very interesting systems because you can actually tune the degree of frustration by changing the counter ion, and you can also tune the bandwidth by pressure, for example, in that case, gas pressure. And of course, there are other families of materials like the ones based on DMIT, I don't know how you say that. I'm not going to try to pronounce the name of the molecule in its full glory, in which there is no checkerboard kind of structure, but they also map on some sort of anisotropic triangular model, at least from a theory point of view. So, as I mentioned, the underlying model is some sort of triangular Hubbard model, and this is a very simplified view of the physics of the problem. Many of you in this room have added all sorts of important ingredients to the model, like a longer range Coulomb. I know that Simone worked a lot on that. Maybe he's going to talk about this later. Elastic lattice coupling, which is really very important. That's the beautiful studies of Michael Lang and his group. Disorder, and so on and so forth. But the sort of underlying simplest spherical cow model is really a triangular lattice anisotropic Hubbard. So turning to the transition metal dichalcogenide bilayers, either with lattice mismatch in homobilayers or twisted in heterobilayers or twisted in homobilayers, they are also described by triangular-based Hubbard models. I'm not sure I'm going to have a lot of time to describe the derivation of that. Maybe I will towards the end of the talk. What's really remarkable in this system is that they can be tuned to a large degree using gates. So here is an example of this heterobilayer experiment at Cornell, in which we have this tungsten diselenide molybdenum ditelluride, which is in a matrix of boron nitride, and there is a top gate and a bottom gate. That's a simplified, of course, picture of this more complex device. And by controlling separately the two gates, you can actually move. So this is a map of the resistance measured as a function of bottom gate and top gate. And you see that you can actually move in this phase diagram. And what you see is regions of very high resistance in red, which you can characterize as insulators, and regions of much lower resistance in blue, which you can characterize as metals. And by varying these two gates, you can actually move from one insulator to another one. As you will see in the following, what these gates do is vary both the filling of the system, so you can control the electron density, but you can also control the band structure. So there is something called the displacement field, which is the difference between the back gate, the bottom gate, and the top gate, which really controls the bandwidth and also some important parameters that I will describe in a couple of slides. So to a large extent, this system, if you want to push it a little bit, realize some sort of quantum simulator of our dear quantum many-body problems. We wrote sort of a review article with André Rubio and a bunch of authors that advertise this point of view. And to a certain extent, this achieves some of Thierry's demands from yesterday. He wanted to have small exchange constants. Well, for example, in the Cornell experiment, it's very hard to do direct magnetic measurements on this system, but you can do dichroism measurements, for example. And in this Cornell experiment, they were able to estimate the super exchange, which is of the order of 3 milli-electron volts. So it's not that large. It's very controllable with these gates that I mentioned before. And you can reach low temperature, which is hard to do in ultra cold, quite hot atomic systems. Well, what this does not completely achieve is having really very large gap insulators. So that was also a requirement of Thierry, but it gives us an opportunity of studying the metal insulator transition. Okay, so in this review article, which I'm not going to deal with much in detail, we sort of emphasize that there is a whole zoo of very interesting phenomena that can be studied in these controllable platforms. And I had an interesting philosophical discussion with Gabe yesterday to know whether this controllable device on demand is going to be the future of condensed matter physics, but we can maybe leave this for the coffee break. Okay, so in terms of low energy models, it can be shown, and this was done in another of a number of beautiful papers by Alan MacDonald quite recently, that these sort of systems, moiré systems on triangular lattices can be described again in a simplified way at low energy by the so-called triangular moiré Hubbard model. So let me flash a little bit more in detail what this model is about. So we have, again, two species of electrons with, if you want, a pseudospin living on a triangular lattice. This pseudospin is actually not quite the physical spin. It's the result of the spin valley locking due to the strong spin orbit in the system. But for all practical purpose, we can just think of it as a spin degree of freedom. And the electrons hop on the triangular lattice. But now what's really interesting is that you see here, the hopping acquires a phase, which is spin dependent. And the pattern of the phase has been mapped here, the positive, the arrow indicating positive phase, according to this pattern here. So this is the Hamiltonian. And many of the parameters of this Hamiltonian are controllable by these gating techniques. In particular, the phase here can be tuned by this, by changing the difference between the back gate and the top gate, and also the overall value of the hopping parameter. And there are many other papers, for example, this paper from the Sarma group and others elaborating on this description. So we call this the triangular moiré Hubbard model for lack of a better name. And as you will see at the end of the talk, this is kind of a nice platform, nice playground for theorists. And my list of materials is by far not complete. There are other materials that form nice triangular lattices, for example, many other TMDCs. There is also an interesting material, which perhaps is not very much studied, which is lithium niobium O2. And there are also examples of adatoms on semiconductor surfaces, where, for example, lead, tin, carbon on silicon 111. And of course, cold atoms or not so cold atoms on in optical lattices. It's not very difficult to form a triangular lattice with interfering lasers. So this sort of closes the list of the materials I wanted to emphasize. Of course, there is not only triangular materials in life to explore the Mott transition. There are many, many other materials in the field of oxides, and there are also many other materials in the field of organics. I can't resist just flashing this, which is another beautiful system, perhaps a little forgotten, in which to study the Mott transition in an absolutely beautiful setting, which is the A3C60 material. Okay, so now I'm going to switch gear a little bit. I'm already pretty late in the talk. And I would like to give you a sort of zeroth order description of the Mott transition. So I'm afraid that all the things that are going to come in the coming 15 minutes are rather old stories. It's been established, I think, over the last 20 plus years, if not 30, that dynamical mean field theory is providing a zeroth order description, but rather comprehensive description of what's going on in the Mott transition, a problem, especially in the higher temperature regime. And in these frustrated systems like the organics, there's been a lot of comparisons of this approach to experiments. So what I would thought useful for this workshop is to sort of review this, not saying that this is the ultimate answer to everything, because as you will see in the second part or third part of the talk, there's a lot of things to do beyond this zeroth order description, but just to set the stage. Okay, so I've already shown this, which is a very general cartoon of what can happen. And when you actually solve the Hubbard model using the dynamic mean field theory approximation in its simplest form, essentially this is what you get. This is the general picture that you are getting. And in particular, you are able to describe the crossover at high temperature and the transition at lower temperature that takes place when you evolve from a metallic state to a Mott insulating state. And this problem has been notoriously a difficult problem. The fundamental reason being that you have to handle on the same footing low energy aspects and high energy aspects. What I mean by that is that if you are here deep in the metal, you have nice coherent quasi-particles. If you actually look at the total density of states of the system, you will see that there is a nice band that has a certain density of states. Here's a cartoon where this band is half filled. And as you crank up interactions, the bandwidth of this quasi-particle goes down. So the range here where quasi-particles exist as a function of energy becomes narrower and narrower. But at the same time, there is spectral weight, which is transferred to high energy excitations. These high energy excitations are very simple to understand in an atomic language, just amounts to take an atom and remove an electron, that's called the lower Hubbard band, or take an atom and add an electron, that's called the upper Hubbard band. And you've already immediately understood in what I'm trying to say that the low energy excitation is best thought of in a language that uses waves and reciprocal space, while the high energy excitations are much more local in space, and they are much easier to think about in terms of particle-like, atomic-like excitations. And it's the fundamental difficulty of the strong correlation problem that you have to handle both the particle and the wave description on the same footing, which is the essence of quantum mechanics, okay? So this is why one of the ways of seeing why the strong correlation problem is actually a difficult problem. And this is why you need the D in DMFT, because this is a theory that does a different job describing the high energy and the low energy, but a consistent job all over the energy spectrum. There is no way you can describe this phenomena by any form of static mean field theory, where the only thing you have is some degree of freedom coupled to a static field. So this is the fundamentally interesting question in this problem. And in a cartoon-like description, what DMFT produces is a description of how the quasi-particles die and how at low energy, as you gradually approach the Mott transition, and how the low energy spectral weight is transferred to these high energy excitations. This is something the spectral weight transfers are ubiquitously seen in all experiments, all spectroscopic experiments on strongly correlated system, in optics, and in many other spectroscopies. Okay, so let's go a little bit more into the details and ask the following question. Here at high temperature, we have a crossover between a good metal and an insulator with sort of fluctuating magnetic degrees of freedom. In between, there's going to be a very interesting set of crossovers from a bad metal to a bad insulator, if you want, and I will come back to this a little later. But let's imagine we can continue to explore this crossover without the intervention of ordered phases, which is where frustration helps us. Well, what happens? What dynamical mean field theory tells us that could happen is that there would be eventually a first-order transition with a first-order transition line ending into a second-order critical point. So if you have a first-order transition, it means that there is a zone where there are actually two coexisting local minima of the energy landscape, which do not have exactly the same energy, the transition line being the one where they do have the same free energy. So actually, if you zoom in, now this is an actual solution of the DMFT equations on this low energy region, you would have a spinodal of the insulating state when you come from strong coupling, a spinodal of the metallic state when you come from weak coupling, and in between a transition line obtained by matching the two free energies. And please observe that the temperature here, which is basically expressed in unit of the bandwidth, is like almost 2 orders of magnitude smaller than the bare energy scales of the problem, which is another hallmark of strong correlation phenomena, that the energy scales that are relevant at low energy are way, way smaller than the bare energy scales, which is what makes the problem difficult. Okay, so this is the solution of the DMFT equations without allowing for any ordered phase as we go to low temperature. And let's ask, what is the nature of this phase transition? So I'm now going to focus on the vicinity of this critical endpoint of the transition and ask what's the nature of the phase transition. Well, these two phases do not correspond to a symmetry breaking. It's very similar to a liquid-gas transition where you can go around the critical point. We are at finite temperature. You can, from a fundamental point of view, go continuously from a metal to an insulator. Of course, from a practical point of view, there is a very serious difference between a metal and an insulator, even at room temperature. I invite you to try on this plug here. So, you know, depending on whether you are a practical person or whether you are a fundamental Landau-inspired theorist, you may say these two phases are the same, but well, don't try this at home, okay? Don't say, Landau told me there is no difference. That would be a little problematic. Okay, but nonetheless, from a theory point of view, and let's say I put my theory hat, there is no fundamental difference. So it's like a liquid-gas transition. We all know that liquid-gas transition are like an Ising, is in the Ising universality class for criticality. So can we give a somewhat more physical picture of this analogy to the Ising problem? Well, this was put forward very early on by Castellani and co-workers and Denis Feinberg many decades ago, where they said, okay, you know, the metallic phase is a phase that is going to have a lot of holes and double occupancies. And the insulating phase is going to be a phase which has very few holes and double occupancies. There should be here a few floating around. So we can think of it, we can think of the insulator as a gas with very dilute concentration of double occupancies or holes. So that would be the gas phase. And this phase, the metallic phase, as more a liquid phase with a lot of double occupancies and holes. So this was elaborated in this beautiful paper by Castellani di Castro, Feinberg, and Raninger many decades ago, where they sort of made an analogy with the Boom-Emery-Griffith model. At the end of the day, what they showed is that this should be in the Ising universality class. And it turns out that from a now controlled mathematical point of view, if you analyze the dynamical mean field equations for this transition, you can actually show that indeed there is an underlying Landau theory, which is that of an Ising or liquid gas transition. And in this analogy, basically, let me skip a few things here. What plays the role of the effective field in the Ising language is basically the bandwidth control of the transition or the distance to the critical pressure, if you think of organics. And what plays the role of the temperature or T minus Tc in the liquid gas transition is actually T minus Tc in the physical problem. More precisely, this field and the distance to the critical part are actually linear combinations of these two things. So the scaling axis at the transition need not exactly align with temperature and pressure. And this has been abundantly discussed in the literature, as you will, and you will see why in a minute. So about 2 decades ago, there were a few papers that actually went on and experimentally tested this picture of the Mott critical endpoint as observed in organics and in oxide being in the Ising universality class. We did this with Patrice Limlet, who was doing his PhD in Orsay in Jérôme's group at the time, and the group of Kanoda. So that was on V203, and the group of Kanoda did it on kappa BDT salts. And so this is just a little bit of travel back in time into V203 physics. Again, this material has this sort of 3 phases we discussed before. This is the paramagnetic low pressure phase, which is hole poor. This is the paramagnetic metallic phase, which is hole rich. And then eventually the systems orders because it's not frustrated enough. And in the kappa ET source, there is an even more interesting phase diagram. Again, these 2 phases, first order Mott transition critical endpoint. I'm talking about the vicinity of this point. But now at low T for this material, we have again ordering, but we also have superconductivity at about 14 Kelvin. So in V2O3, what Patrice Limlet did in the old days is actually to measure conductivity versus pressure. You see that above the critical endpoint, which is at very high temperature in this material, because it's an oxide, the critical endpoint is at 450 Kelvin. You see this sort of smooth increase. But now as you go close to TC, this thing becomes S-shaped, very characteristic of another parameter of an Ising model. There is a jump as you go below TC. You can even evidence the hysteresis. And what we did at the time is we used the properties that we know for the Ising model to represent these different quantities. So this is just directly expressing the different data. We were able to measure the critical exponents of the transition, the sort of conductance minus critical conductance versus T over TC is associated versus, sorry, P minus PC, where P is pressure, is basically a measure of the delta exponent associated with the response of the magnetization to an effective field. In the Ising analogy, we found that delta is close to 3, which is the mean field value. We even argued that if you get very close to the transition, you get back 3D Ising, which is delta equal 5. That was not so obvious from the data, but it's sort of there, and then so on and so forth. And we were even able, and that's, I'm actually pretty proud of that, we were even able to scale the whole set of data onto the universal equation of state that you would expect from an Ising model. And you know, as far as data collapse go, I know you can still make a lot of data collapse when you want them to collapse, but this is not so bad. Okay, so in Canada's group, the same sort of analysis was done on BDT source, and well, it came out with a surprise, which is that there is also a beautiful data collapse, but the exponents that come out of this analysis are actually very different from the ones you would expect from the Ising model. Delta, for example, is close to 2, as you see here. Beta is close to 1. Gamma is close to 1. And especially for delta, the thing which is really surprising is that not only they do not really fit the Ising model, but they are also very different from any known delta exponents from any known transition. Delta equal 2 is extremely surprising, as you see from comparison to these well-known StatMech models. So this was a subject of long debates, and perhaps this is the first thing we encounter in this talk, which is perhaps not fully resolved at this stage. This puzzle has received a few explanations. So a few explanations means probably a few too many. Some very elegant. There is an absolutely beautiful paper by Jörg and co-workers, which is here, in which Jörg said, okay, well, you guys are saying that the conductivity couples to the order parameter of the Ising model, but are you sure about that? There is another operator in the Ising model, which is the energy density, which has a different scaling dimension. And what about if it's the conductivity is a superposition of these two things? And with this beautiful idea, these authors were actually able to explain this delta equal 2 or almost 2, close to 2, which I find a very elegant argument. There are also, this paper also emphasized something which has been studied intensively, in particular in the group of Michael, which is that the coupling to the lattice is actually very, very important in this problem and induces long-range interactions, which make it somewhat more mean field. That doesn't explain delta equal 2, but there are other possible explanations floating around, a little bit more mundane, but still interesting. In the group of my friend André-Marie Tremblay, they pointed out the importance of the subleading corrections to the Ising description, and in particular, the possibility of a very strong rotation of the scaling axis between field and distance to the critical point and temperature and pressure. And they also claim that this could explain the BDT experiment. So I leave this with, I leave you with this. Maybe this problem is not completely nailed down, but I just wanted to put back this somewhat time-honored question in the. So now what I'm going to do is I'm going to not cool the system, but actually heat the system and focus your attention on things that are happening at higher temperature. So we've seen here everything that I was talking about is a pretty delicate analysis around TC here. Now we're going to go to much higher temperature. So you would say, okay, we go to much higher temperature, everything should become a little more classical and perhaps then a little bit more boring. Well, it turns out that this is apparently absolutely not true, and that there is something really fascinating that is happening here. And we've known for a very long time, since the early day of the DMFT equations, that there are very interesting crossovers here. We now know that these crossovers are also associated with things happening in the electronic compressibility. This has been called the Widom line. It's a long story that I'm not going to describe in details. But the thing I would like to focus your attention on is that in this regime, it has been shown that just by solving the dynamical mean field equations, that actually the conductivity ratios seem to obey some sort of quantum critical scaling. So this is very surprising because we are at very high, well, relatively high temperature, not that high, but like 2 or 3 times TC, and certainly not in the close to T equals 0. But it's there in the mathematical, in the computational solution of the DMFT equations, which at the end of the day are not very complicated equations. So this was put forward in a set of beautiful papers by Vlad Dobosavljevic, Hanna Terlecka, Jakša Vučićević, and co-workers. Very much a work from Belgrade, Serbia. And what they showed here, so these are calculations of the resistivity versus temperature in this higher temperature regime. You see that there is an insulating branch, there is a metallic branch. You've seen this in many, many systems that display metal insulator transition. And they were able to scale all this data. But now the scaling is completely different from the one I showed before. It's a scaling that involves the T over some energy scale T naught and some dynamical critical exponent. So something that you would usually do if you are in the quantum critical regime near 0 temperature quantum critical. So to this day, in my opinion, the fact that out of this theory, you get quantum critical scaling at high temperature is not completely understood. These papers argued that apart from the plane of the physical parameters of the model, which has this phase diagram, there could be an additional deformation of the model in which you can drive TC to 0 that would control the high temperature regime, but eventually for this deformed model correspond to a quantum critical point. But this is just a speculation. Nobody has really been able to actually show this microscopically. So this is kind of open. But being there in the theory, this was again put to the test in actual experiments. It's been known for already a couple of decades that if you look at transport on sort of a global scale, the dynamical mean field theory does a pretty good job at describing resistivity versus temperature for the kappa organics. This is an early paper we wrote again with Patrice Limlet and my former student Serge Florence on this topic. But in recent years, this was pushed much further. And this is a paper, again, from Canada's group, in which they tested. So now we live here at much higher T, you see in the sort of 40 to 100 Kelvin range, and accumulating a whole set of conductivity data here, they were able in actually different materials to scale again the conductivity data, but this time using this quantum critical scaling. And this was rationalized and extended to optics and put on a very broad footing in a set of beautiful papers in Martin Dressel's group, involving also one of our organizers, Andrei Pustogor. And they put forward the notion that you can rationalize all these things, thinking about temperature and electronic correlations. And when you put all the correct energy scales together, what happens is that when you think of a very hard material where energy scales are very high, like V2O3, you actually explore here the vicinity of the critical endpoint, But when you take a much broader view, which is what the ET source allows you to do, because these materials have much lower energy scales and are also much softer, you can actually explore much more broadly this very rich crossover at higher temperature. So I will leave you with that. I'm not going to describe this much more in detail. I will leave you with this question of quantum critical scaling at high temperature, which sounds like an oxymoron or a paradox, and in need of an explanation. Okay, so now I would like to switch gear a little bit. Everything I've been saying up to now has been known for quite a while. And I would now like to tell you things which are much more recent from the theory point of view and also the experimental point of view, and tell you some things about the moiré triangular Hubbard model, and then go back at the end of the talk to just the plain good triangular, even half-filled Hubbard model, and show you some very recent computational results. But if you have questions on the first part, this is probably a good time to ask them. Yeah.
What is the expectation for frequency?
Yeah, that's actually a very good question. And did you try that in your, let me return the question to you. Did you try that in your data? Mm-hmm. Well, I mean, you know, if you really have, well, the answer is simple. Now, reality may be quite different. If really there is quantum critical, you see, I'm an agnostic on this. I look at this with amazement, and I still need to be convinced. If you actually have genuine quantum critical scaling in the system, we know what happens. You open Subersage-Lev's book, right? And you will read that most of the time you have h bar omega over kt scaling. And in cuprates, for example, there are actually a few recent papers on arXiv, even you know, in the few past weeks about this. There is beautiful omega over t scaling in the quantum critical regime or strange metal regime of cuprates. So, you know, one can take inspiration of this and see if you're optical, we can discuss this, because I scaled myself cuprate data recently. So, you know, you should expect h bar omega over kt scaling. Does that apply even to the DMFT solution for optics? I don't know if this has been looked at in this regime, actually. It's a good question. Okay, so if there are no further questions on this part. Yes.
You pointed out that the transition temperature of the endpoint is rather small.
Yes.
Can one understand this?
Yes.
You have the London.
Yes, yes.
What is
yes, yes. It's basically the reason it's rather small is because the difference in free energy. Fundamentally, it's because the difference in energy between the metal and the insulator at zero temperature goes like U minus UC squared. Mm-hmm. And so, you know, to estimate TC, you have to match this energy difference to the entropy difference. And this leads you to an estimate, which is really quite a small scale.
Good.
By the way, let me just ask things. So this, what controls TC is the entropy of the insulator. So, right, because basically TC is some ratio of energy difference to entropy difference, okay? So if you make this entropy difference much bigger, then you can raise TC. And this is what happens in SUM models. If you extend the degeneracy, you will push TC. We actually know how it scales. In my memory, I think it scales like square root n, but I need to check that. Wrote a paper on this 20 years ago. We know how it scales, and actually this has been verified in calculations. And you know, there are systems that realize SU and Hubbard models. It would be quite interesting to look more into this. Yeah, yeah. Yes, yes, it is. No, I mean that. Yeah. Yes, yes, yes. So again, this is not my work, so I don't want to elaborate more. I'm sure there are other ways to scale data. This one in this regime. I mean, the Ising thing is a done deal. I mean, we know how to scale things. Well, except for the question I was mentioning. The higher temperature regime, to me, is still a somewhat open problem. So anybody is welcome to try other scaling forms and even criticize scaling in this system. It's just an interesting open question. Okay, so in the minus 15 minutes that I have, I am going to tell you a little bit about more recent work on triangular systems. So I have emphasized these different experiments on moiré systems, and there again, a number of evidence signatures of strong correlation physics have been put forward. This is one, for example, this is from the Columbia group, the twisted homobilayer tungsten diselenide, where as a function of temperature and filling, which again can be gate controlled, there is a transition between a low resistivity metallic state and a high resistivity insulating state. And even more beautifully, in this regime here close to the insulator, it was observed that transport is sort of T-linear, and you may want to call this a strange method, like in cuprates, where at farther away from the insulator, you get something like a T-square family. Okay. In this experiment, which is the Cornell experiment on heterobilayer moiré, again, resistivity versus temperature was measured, and you see something that looks extremely similar to all the curves I've shown you before, displaying a very nice metal to insulator sort of behavior. And as Jose mentioned, the first thing that's going to happen in the next slide is that the experiments are going to try to scale this data. And they managed to scale the data quite beautifully, as you will see. This is a little band structure cartoon, well, actually calculation, that shows how by changing the displacement field, the difference between the top and bottom gate, you can actually change the band structure. You see here, you can get a very narrow bandwidth band, hence making it very happy. And here you can get a somewhat higher bandwidth and so on and so forth. Okay, so I'm going to skip a number of slides in which I was planning to sort of derive why the twisted triangular model gives you this twisted moiré-Hubbard model with a phase. So watch the show. I'm going to basically skip them. This is due to spin valley locking. And you know, this is the effect of the displacement field. With zero displacement field, you have a single band. With displacement field, you lift the degeneracy. And the bands, because of the spin valley locking, have a definite spin character. At the end of the day, you get this moiré-Hubbard model with a tunable phase. Okay. So with a bright graduate student from Andy Millie's group in Columbia, Jiawei Zhang, and a bunch of collaborators, there was first a Hartree-Fock study of the magnetic phases of this problem. So this is the half-field triangular Hubbard model, but now we have an additional twist, which is this angle phi. So this is just Hartree-Fock, okay? So if we are at phi equals 0, which is the standard triangular lattice, what Hartree-Fock tells you is that there is a metal insulator transition in this system from a system that has no magnetic order to a phase which has the famous 120-degree sort of spiral antiferromagnetic order characteristic of the triangular lattice. We actually know better. We know that here there is a spin liquid phase, or at least a different insulating phase. I'll show this to you in a few slides. But now this is just to illustrate the fact that phi, the displacement field, give you an additional handle. And what you can do is that you can tune with phi this magnetic transition down to a special value phi equal pi over 6, where it now happens just at u equals 0. And this is because at phi equal pi over 6, the Fermi level lives on a Van Hove singularity. So the critical u is 0. And there is a rich zoo of magnetic phases here. There is a ferromagnetic phase and so on. This is just Hartree-Fock. Real life is actually even more interesting. So the next thing you can do is actually you can study this problem with dynamical mean field theory. You shouldn't expect from this to be able to describe the spin liquid phases, at least not in the single side DMFT picture, but you can get a much more precise estimate of these transitions. And you see here how the critical U for the ordering transition was displaced by about a factor of 2 when you go from Hartree-Fock to DMFT. So that's something that we did with the same people that I mentioned before, and I'm very grateful to have been associated to this work. But of course, if you want to understand more than just the 120-degree ordering, you need to use more sophisticated computational techniques. And Alex Vitek, who's an absolutely bright person who was a postdoc at CCQ, and he's now a junior researcher at the Max Planck Dresden, studied this using hexagonal organizations on, of course, whatever size can be done, but he can do the bigger sizes in the world. So that's pretty good. And what you see here is a more interesting sort of phase diagram. So happily, the overall structure of the magnetic phases is in pretty good agreement with what I showed you before. This is, of course, finite size, so it's a little bit hard to extrapolate to what happens in the thermodynamic limit. But let's say that just from the level crossings that occur in the ground state, there is some indication here at the boundary between the ordered phase and the 120-degree order that perhaps there should be some sort of different state at the boundary. Okay.
That state seems to be particularly strong at small u near these.
A small phi, you mean?
Yeah. Small u.
Oh, near the Van Hoff. Yes. This is a very interesting region. This is not fully explored yet. It's a very interesting region. Okay, so I will continue a bit on the magnetic phase diagram, but I want to take a little detour.
We got 9 more minutes in total.
Yeah.
So if we want to have 5 minutes, and
yeah, I know.
Another 5 minutes before we talk.
Well, I'll try my best. Okay, so as I said, these transport data have been scaled. They've been scaled theoretically. So with Jiawei Zhang, we actually did some. She actually did some DMFT study of this twisted Hubbard model as a function of phi, obtain resistivity data. This resistivity data can be scaled exactly in the same way as before. The beautiful thing, I missed an important slide here, which is the actual experiment scaling. So sorry about that, but the actual experiments have been scaled actually before this theory work, and the scaling is similar. Okay, so I will try to wrap up the talk in just a few minutes. And what I want to do, just to wrap up the talk, is to go back to the simplest case, which is the case phi equals 0 half field. So just the good old triangular Hubbard model at half filling as a function of u, and try to explore what's going on here when you cross over, when you have this transition from a metal to a 120-degree insulator. Well, this problem was studied in a set of beautiful papers just a few years ago, like 2 years ago, in particular by Mark Zaletel and his group. And what he showed is that between, so this model has a phase transition at 0 temperature between a metal and an insulator, but this transition is not directly from a metal to the 120-degree ordered insulator. There is clear evidence that there is an intermediate phase in the range of coupling, which is between about 8 and about 10, into a non-magnetic insulator phase. The exact nature of this non-magnetic insulator is still the subject of debate in this work, which is which is DMRG at 0 temperature. What was suggested, and with some evidence, is that this ground state is actually a carrier spin liquid. What you will see in like a slide is that the story may be actually a little bit more complicated. So we wanted to extend this work to finite temperature. And this is actually a very fundamentally important endeavor in the field of the quantum many-body problem for the following reason. And this is an occasion to give you a little bit of an overview on where computational methods are going. Until a few years ago, there were really two worlds in the world of computational methods. There were a class of methods that were very good at addressing 0 temperature ground state issues whenever accessible, let's say in low dimensions, using tensor networks methods and DMRG. And then there is another class of methods which you want to think about as approaching the problem from high temperature, where the fundamental principle is locality, while here the fundamental principle is controlling entanglement. And this, of course, is the world of Green's function methods, and especially DMFT and extensions to cluster DMFT. And until recently, there was sort of a divorce between these two methods. And in recent years, I think that a very, very interesting development is that these two classes of method have started to talk to each other. So there is some sort of handshake which is taking place in the field in which the tensor network DMRG methods are now coming from. Extensions are able to study finite temperature regimes. And of course, extensions of embedding methods are able, by going, for example, to large cluster DMFT, to actually go down in temperature. And there is a handshake that can be done where we can see the same physics using different methods. There is also a different class of methods that try to address the problem in this way. And this would be diagrammatic Monte Carlo methods and so on. So this problem is now getting cornered from all sides so that one can make progress on different fronts. And this is the result we got using the so-called minimally entangled typical thermal state method, which is a combination between sampling methods and tensor network methods. So this is the work of Alex Vitek, where we studied as a function of U this transition between the metal, the unconventional insulator, and the 120-degree insulator. And these are the various structure factors at different points in the Brillouin zone. I don't have the time, obviously, to enter into any details. What you see here is the growth of the chiral spin correlations as a function of U. So indeed, there is increasing chirality. This is the increase of the 120-degree order, which eventually wins at large U. But there is also a sort of intervening ordered state, which has sort of nematic spin correlations that take place in between. And it's not totally clear whether this intermediate phase is a chiral spin liquid eventually, or whether it's a state in which there is both chirality and another type of magnetic order. Another thing we did in this work, and this is the interest of going to finite T, is we could reveal in this two-dimensional system the famous Pomeranchuk effect, which is actually an early prediction of single-side DMFT from like 30 years ago. Pomeranchuk effect is the fact that you can make a liquid to become a solid by heating, which is sort of a remarkable phenomenon, which is due to the fact that the solid, or the localized Mott state, has more entropy than the liquid. We showed this from single-side DMFT many, many decades ago, and this is present in this triangular lattice Hubbard model. This is also realized experimentally in TBH. Okay, so that's the end of the talk. Sorry to have been so long, and the punchlines are here.